And we are live. Yay. So today we're going to talk about matrices, and the basic way to think about this lesson is just mathematicians got lazy and they needed to work with a lot of numbers all at once. So they came up with their own math so that they could work with a lot of numbers all at once. That's it. That's what we're doing today. We're taking what we do with single numbers and transferring it to like a lot of numbers. So when we're in a lot of number world. That's fancy math speak right there. When we're in a lot of number world, we have these things called matrices, which sound fancy, and I used to be scared of them. I avoided learning about them at all costs, but really matrices are just tables of numbers. So just like we can say like x is equal to 2, we could have a variable x and it's equal to a number 2. We can have other variables. So in this case, the variable a, and this variable is equal to a matrix. And the matrix literally looks like a group of numbers surrounded by square brackets. That is the matrix. Not too bad. Just square brackets, bunch of numbers. I would have liked if they had commas in there, but no, you just have spaces. You can see this matrix has 3 columns and 2 rows. And those are for once, those are actually the proper mathematical terms, columns and rows. So you can see why I talked about matrices like a table. And each of these numbers inside a matrix, it's called an element. Everyone good so far with the notation? All right. So when we have these elements, we're going to have another bit of notation, which is you notice here that this element, it's the second row and the second column. So when we're referring to elements, we use this notation right here. We take the name of the matrix and then add subscripts. The first one for the row, so the second row, and the second one for the column, the second column. So that's most of the notation we need. There's a couple of fancy words that you might want to know because we're going to use them a lot. The first has to do with the columns and rows itself. So we call the columns and rows the dimensions of the matrix. So this matrix right here, 3 columns by 2 rows, we say that its dimension is 2 by 3. It has 2 rows by 3 columns. So we put the rows first, the columns second, and we say this is a 2 by 3 matrix. That's how we say it. And that is the dimension of the matrix. Now for every 2 by 3 matrix, we could literally just we could flip it. We were like, okay, we can go from 2 rows and 3 columns to the transpose of the matrix, which just means we go to 3 columns by 2 rows. Actually, no, 3 rows by 2 columns. So go from 2 rows, 3 columns here, to 3 rows, 2 columns here. And here's how it looks. So before we had 1, 2, 3 in the horizontal direction. Now you see we have 1, 2, 3 in the vertical direction. So it's literally like we had a matrix like this and we flipped it. So it's like this. So the transpose of a matrix is just you take the dimensions and you flip them. Sound good? We have this little comma here. This is read as A transpose. And it just, yeah, it means, hey, there's a matrix over here that we defined as the variable A, and A comma, that's read as A transpose. That just means take the matrix, flip. So you just reverse the rows and the columns. Cool. All right. So there's another special bit of vocabulary that we need to know, and it's exclusively for matrices where one of the dimensions, either the row or the columns, is just 1. So, for example, we have this matrix here where it only has 1 column. So that means it has a special name. The name that we give to this matrix, it's called a vector. A vector and we give it a different notation. So instead of a capital variable name, we just give it a lowercase variable name. You can think of it as a vector is less big because one of the dimensions is just one. So we give it a lowercase name. And when we denote like an element in a vector, we don't need to denote like the column number and the row number, because one of those is always going to be one. So here we said A2 space 2, because second row and second column. And over here we're just saying, V2, because it's just, hey, you don't need to worry about one of the dimensions, it's just one column. Again, either the rows or the columns can have dimension 1. So over here, we see another vector. This time I called it W. Here, there isn't just one column, there's two, but there's just one row. So it's still a vector. Sound good? All right. And again here, W2, because we don't need to specify one of the dimensions, as it's always just one. So that is the intro, basically, to matrix notation. That wasn't too bad, right? So keywords again, matrix, dimensions, rows and columns, this bit of notation, transpose, and vectors. Now, the next thing we're going to do with these matrices, remember what I said, mathematicians just invented matrices so that they could work with a bunch of numbers at the same time because they were lazy. And that happened to benefit programmers, by the way. When I first learned about matrices, I was like, this is like a programming concept just disguised in math. Programmers are even more lazy than mathematicians, as you'll soon see. So what we're now going to do is we're going to create operations to mess about with these matrices. Just like we have operations like, 2 plus 2 equals 4. Let me write that out. I'm sure that's a valuable piece of information. Just like 2 plus 2 equals 4. We can do operations with these matrices. Now, the first operations, they're very easy. They're called element-wise operations. Remember these little things, they're called elements, like the numbers within the matrices. And element-wise just means to each element. I'm going to explain this with an example. Let's say you're doing addition of two matrices here. So 1, 1, 1, 2, 2, 2, that's one matrix, plus 2, 2, 2, 1, 1, 1. I take the first element here, add it with the first element here. You can see it has like this light green color. So 1 plus 1, 1 plus 2 equals 3. Then I take the orange one. So the second element here, second element here, 1 plus 2 equals 3. 1 plus 2 equals 3. And now second row, 2 plus 1 equals 3, 2 plus 1 equals 3. And here, the last element with the brown underline, 2 plus 1 equals 3. Pretty straightforward, right? So note one thing. When we do element-wise operations, it's the same size in, same size out. By that I mean, if you have a 2 by 3 matrix here, 2 rows by 3 columns, then you have to add it to a 2 by 3 matrix. So both of these have the same dimension. Like so. And then the output that you get is again 2 by 3, 2 rows by 3 columns. Because by definition, you have to do element-wise operations to each element. If you tried adding like a matrix with, a vector like this, 1, 2, 3, it just wouldn't work because like you can't do it to each element because like all of these don't have any elements to go with. So again, these are just arbitrary rules that mathematicians defined that this is the way elementwise operations work, just like 1 plus 1 equals 2. It's just what mathematicians decided. Now, as you can imagine, it's the same thing with subtraction. So we have minus here, 10 minus 7, the first element, that equals 3. 9 minus 6, the second element, that equals 3. 8 minus 5, the last element, that equals 3. Again, same size in, same size out. With multiplication, I think you're starting to see the pattern. The only difference is we have these special symbols. So technically, mathematically speaking, we don't use like a cross or, that dot symbol for multiplication like we would with, 2 times 2. Instead, we have this open circle. That's the mathematical symbol. Or if you're watching like Coursera courses, you might see like dots and then this asterisk. That's because in some programming languages, that's how you represent the multiplication. But it's pretty simple. And here, I added in random non-integers just to show you, hey, you can have a decimal. That's fine. You can have pi. That's fine. So 1 times 5 equals 5. 9 times 0 equals 0. 1 times pi equals pi. You get the idea. Just match up all the individual elements. And unfortunately, we don't really have a symbol for division. So what you do is like to divide something. So let's say 2 divided by 2. Instead of saying 2 divided by 2, you could also say 2 times 0.5. So that's what we have to do. It's like 0.5 times 2, that's 1. 0.5 times 4, that's 2, and so on and so on. One exception is when you are programming again, you can have like a dot slash. It's like you could say 2 over 3 in just one number land. So when you're in a group of numbers land, you could say like, 1, 1, dot slash, and then 2, 2, and you would get 0.5 and 0.5. Not too hard. Yeah? Alright, so let me restart. Again, this is just from programming. That's why we have the symbol. You might see it in Coursera courses on AI or something. So the next thing that we got to do is talk about something called scalars. So scalar is a special word for like all those pieces of data that are just one piece of data. So x is equal to 2. That's just one thing. It's not a group of numbers. It's just one number. Y is equal to pi. One number. Z is equal to negative 4/3. One number. Scalar just means anything that is one number, not a group of numbers, unlike matrices and vectors, which are groups of numbers. Yeah? So when we do scalar vector operations, that means something like 2 times, this matrix, or 2 plus this matrix. And it's just the same thing as before. You just apply the scalar element-wise. So 2 times this matrix, well, 2 times the first one, that's 2. 2 times the second element, that's 2. 2 times the third one, and so on. And same thing here. So 2 plus the first element, that's 3. 2 plus the second one, that's 3, and so on. So it's a pretty simple concept. Yeah? So up until now, we're not getting into anything weird. Okay, this is as you'd expect. Now, the next concept is the most important part of this lesson, but it's also the most weird. It's a mathematical operation that seems very random. And the reason it seems random is because mathematicians decided, hey, this is what we want today. This is what we want to do with our groups of numbers. This is how we want to play with them. So they defined a mathematical operation that seems a bit weird, but it's necessary. So we're gonna have to learn it. This mathematical operation, it's called the dot product. Now, it's different, keep in mind, from this multiplication. Okay, this is like an open circle. So that's different from, and this is called Elementwise Multiplication. That's different from a dot product, where you use a dot. And it reminds us of the dots we use with regular scalars. So 1 times 2 is equal to 2. It's just like that dot, except the operation that it denotes, that's different. So we're going to do something weird with this, all right? So bear with me. So you have these two matrices, vectors, and one is 2 rows by 1 column, the other is 1 row by 2 columns. Now notice, important, okay? Let me use pink. 2 rows here, 2 columns here. The number of rows of the first matrix or vector, it has to be equal to the number of columns of the second. Otherwise, this operation is not defined because mathematicians said so, okay? This is like a 1 + 1 = 2 rule. It's one of those rules. Now, I'll explain what we're actually doing. So what we're going to do is we're going to take the first element of the first vector or matrix, match it up with the first element of the second one, and we're going to multiply them together. As you can see, that's in light green. Then we're going to take the second element and multiply with the second element. As you can see, that's in orange. If there was a third element, we'd do the same thing, and we just keep matching up the elements and multiplying them together. Then what we do is we add together the products. So we add together the results of all these multiplications. So 1 times 1, these two, that's equal to 1. 2 times 2, that's equal to 4. And then you add together the products. And what you get out is 5. So this, all of this business, that's something Sal Khan says. I feel proud. I'm copying Khan Academy. All of this business, that is equal to this number. So you do this operation, you get out this. Yes, I know. You technically have these two vectors going in, and you have a scalar getting out. Now, that's an interesting concept. Just keep that in mind for later. Hey, it seems like we have a lot of data, a lot of information over here, and we have less information over here. We're going to come back to that later. But I did want to give you a real life example of how we could use a calculation like this. So what are those crazy mathematicians doing? Why do they want us to do this? Well, if you think about it, pretend that this vector, it represents two athletes, okay? Specifically, it represents here the number of games that the first athlete won and the number of games that the second athlete won. So like, let's say the first athlete, he does swimming and he won 1 swimming round. The second athlete, she does badminton. She won 2 badminton games. And over here, this is the amount of points that they earn per game that they win. So the first athlete who does swimming, he wins 1 swimming round and he gets 1 point for each swimming round that he wins. So 1 times 1, the number of games times the number of points, that means he got a total of 1 point. The second athlete, she's playing badminton. So she won 2 badminton games. She got 2 points for each game. See, she got 2 times 2, 4 total points. So we add those together and we get the total number of points that all the athletes won. Now imagine you didn't just have 2 athletes, you had like, 10,000 athletes. That would be pretty nice. You get the total points won for all the athletes by just multiplying like one operation. That's pretty cool. That's pretty efficient. That's pretty neat. So that's an example of why those crazy mathematicians, they defined this the way that they did. Make sense? All right, let's do another example because this is the only foreign concept. This is the only hard concept. And remember this, okay? Num rows of first must equal num columns of second. 2 rows here means 2 columns here. You have to have it, otherwise it won't work. So let's go on to the second example here. Now, does anything look strange here to either of you guys or gals? Paris?
But there's 3 values on the first vector and Wait, no, there's 4 values in the first vector and 3 values in the second.
Yeah. So we have 4 rows here, but we only have 3 columns here. That's not gonna work because, that's what we said above. You can't do this. You have to have the number of rows of the first equal to the number of rows of the second, number of columns of the second. So that's very silly on my part. I wonder why I did that. So I'm gonna have to fix that. I'm getting so negligent, guys. Let me just put in this number that I somehow knew that I needed to put here accidentally. That's fine. So let's go through the calculation. All that we do is we match up first element here with the first element here. 2 times 3. Multiply them together. Second with second, 5 times 2. Third with third, 8 times 1.5. Again, keep in mind, they don't have to be integers. They can be decimals, whatever. And then finally, 3 times 4, the last number. After we've multiplied everything together, we can now start to add. So 2 times 3, that's going to be 6. 5 times 2, that's going to be 10. 8 times 1.5, that's going to be 12. And 3 times 4, that's also going to be 12. Now 12 plus 12 plus 10, so that's 24, 34, and 6, that's 40. And we add everything together, and that's what we get. That's the output. So this times this, all of this business, that means you get this out. Aren't I great at addition? I feel proud. That was quick math right there. All right, I'm gonna throw you guys in for a loop. Are you ready? I'm gonna be able to, just because. Let's say we now have this over here. Now this is weird, isn't it? Like up here, we just had 2 vectors. Up here, we just had 2 vectors. What's going on here? We have like a matrix and we have a vector. And they seem to be like eerily color-coded, these things. It's almost like there's something going on here. It's almost like this nonsensical mess actually makes sense somehow. Don't you guys think? So let me go back to the rules we had. Okay, this is what we must do. We got to go back to the rules. What do the rules say? The num rows of the first must equal the num columns of the second. So we have 2 rows in the first over yonder, and we have 1 column in the second. That's not going to work. We're going to need to change something. What can we change? What can we change? I know what we can change. Let's take this matrix, this vector technically. Let's take the transpose of that. So we're going to flip it horizontally. Let me fill this in here. And let's flip it. So instead of having a vector with 1 column, 2 rows, I'm going to take the transpose. This is something we're going to have to do a lot when we're coding. Reorient things in the right position. I believe it was like this, and if not, well, that's unfortunate. I messed up my color coding. But hey, look what we have now. So we don't have 1, we have 1, 2. We have 2 rows in the first and 2 columns in the second. And if you see, num rows of the first is equal to the num columns of the second. Hey, we just solved one problem. We just solved one problem. However, we still have a problem. What's going on? Like, okay, the rules say it's fine. It's fine now because we took a transpose. But how are we supposed to multiply like this matrix with a vector? This is weird. Here's what we're gonna do, okay? This is gonna seem weird at first. There's 2 steps. The first step is that we have to break up what we're multiplying. So we have to break it up into either the first row and the second, or in the first column and the second. We're going to break it up, in other words, into individual vectors. It's like we're slicing down this matrix into individual vectors. Now, I think that I drew these in the wrong orientation. So close your eyes for a second. We're going to do it from scratch, all right? This is improv math right here. It takes talent. Pretend you never saw this. That is a sin. So we're going to break it up in real time. This is going to take skill. I don't have my notes to rely on. You think I'm going to be able to do it? Yeah, okay, you guys believe in me, that's fine. Cool, that's nice. Okay, so here's what we're going to do. We're going to slice this down the middle like this. Why am I slicing it like that? Because I need 2 rows, okay? I need to keep 2 rows, and I need 2 columns here, because the num rows of the first must equal to the num columns of the second. So over here, I have 1, 3. So this is in blue. And I'm going to color code these so they make more sense. Give me just a second. And that makes sense. And there we go. So I'm going to take 1 and 3. Orange first, then blue. 1 and 3. So that's my first vector. Notice I just got the vector by slicing up the matrix into individual components. And then I'm going to multiply it by the rest of this. Hey, now we know what to do. We know what to do now. So we can just say, okay, just multiply 1 times 4. And, we get 4, first element times first. And then multiply 3 times 5, second element times second. We get 15. And once we do that, we can add it together and get the final answer over here, which is 19. All right, so that's what we did from the first row that we split up, okay? Then we're gonna do it again. So now we have 2 and 4, we have the right half. So we're gonna go, okay, make a new vector, 2 and 4, 2 and 4. And we're still multiplying it by the same business over here. I think I can just copy paste, like so. And you know what we do, first times first, second times second. So we got 2 times 4, that's 8. And 4 times 5, that's 20. Marian's nodding, sorry. Reese, you're nodding like, yeah, I already know, you don't need to write it out. I've already done it in my head. Come on, I'm not lightning fast, you gotta keep up. All right, 8 times 20, that's 28. There we go, a bit slower than Reese. Close your eyes again, I gotta erase the results. Erase. You didn't see that. There we go, it's just darkness inside. There's nothing there. So here's what we did. Go away, green. Here's what we did. We split it up into half and half, but we could have split it up into like, one here, and there's another column. The entire point was keep 2 rows by 2 columns. So over here, we have this left column, and that gives us this result that we got on the left. And with darker green, we have this right column that gives us this result on the right. Make sense? So since these results came from like a orientation that was like, okay, left then right. What we do in the end is we just put them back in the order that we got them. So we put the 19 on the left, and then we put the 28 on the right. Not too bad, right? So we just split it up. We had to do some problem solving there, and we're gonna have to do that kind of problem solving again later on when we're figuring out, okay, in coding, why is this giving us errors? It's because we got to figure out how do we multiply these together so that we can get the number of rows of the first to be equal to the number of columns of the second. Whenever we have a matrix, we just split it up into multiple vectors. I karate chop that until we get it in the right orientation. So we split it up left and right. We could have had a third one here. There would be no worries. So just so long as the number of rows of the first is equal to the number of columns of the second. We could have split it up like that. So left one here, get this output, right one here, get this output, and then you put the left one on the left, right one on the right. Makes sense? All right, we're gonna skip forward past the last example because it's just the same thing again, but that time we were slicing it horizontally, just because that's the thing that worked out in the end. But let's just quickly run the last thing with gradients of a vector. Now, this is basically a way to store partial derivatives, which is something I talked about in the last lesson. If you didn't see it, I'm not gonna talk much about it, but basically, and so you have a function that has, two variables here, x and y, and the output is x squared y, yeah? Now, in the last lesson, I wrote this as z is equal to x squared y. It's the same thing, just different notation, right? This is a function notation, this is like variable notation. If we take what we call the partial derivative, which is represented by partial f by partial x, what that means is if we move the x variable just a tiny change this way, what happens to the output? What happens to f of x of y, f of x and y? So if we make a tiny change here, what's the effect here? And remember, for partial derivatives, we're isolating for the effects of that one variable. So we're saying y, we're going to lock you in place. So let's say like y is always going to be equal to 2. And x, we're going to move from like say 1 to 0. To 0.9999999. It's just a very tiny change. What happens to f of x and y? Real life context, the speed that you run at is your stride length squared times your height. So we say, okay, if you just increase your stride length just a little bit, how much does your speed change, the speed at which you run? And if we're going to test that, obviously, like think science, you got to isolate your variables, So we're going to lock this in place. We're just going to modify x 1 at a time. Here's what the gradient does. Here, we wrote out partial f by partial x, and we could write out partial f by partial y. But that takes a long time. Mathematicians are lazy. That's the rule of this entire lesson. So imagine like you had f of theta, where theta was like theta 1, theta 2, theta 3, theta 4, theta 5, and all the way up to like theta 100 or theta n or theta 1000, like anything. You don't want to be writing like, okay, theta, partial f by partial theta 1 and then partial f by partial theta 2, and like it takes too long. So the gradient of a vector is basically a storage container for all of these derivatives, all of these partial derivatives. So gradient, it's represented by this upside down triangle, nabla or del. Those are the two names, nabla or del. And it stores all the partial derivatives of the function. In other words, if you have f of theta, and theta is equal to like all of these individual variables, it's going to store the partial derivatives of f with respect to all of these variables. Here's an example. So nabla f of x and y, it's going to return a vector that is partial f by partial x, that's the first variable, and partial f by partial y. That's the second variable. Or in the case of data, so f of data has all of these variables, just like, two variables here. Here you have n variables. And nabla, f of data, it just returns the partial derivative of f with respect to each of these variables. So it's saying, if you move, x a tiny bit, how much does f change? That's the first one. Then if you move y a tiny bit, how much does that change? Second one, and so on and so on and so on until you get to the last output variable. Get it? Storage container for all the partial derivatives. Any last questions? We have 1 minute left. No? All right, so I know this felt a little bit abstract. Luckily, what I did was I split the next practical lesson into its own thing, and it's going to be so fun. It's basically a mix of math and philosophy. Like, I'm not even kidding. Math and philosophy. I'm going to be talking about, like, what does it actually mean when we have like this weird kind of wacky function with like two variables in it? What are all those real life analogies? How do they fit together? So I'm going to be very excited to see you then. It's going to be visualizing. We're going to visualize everything. Visualization is really important in AI. But here, it's just a bunch of notation plus a bunch of random things that mathematicians decided to do. So that's the lesson.